Let us now discuss about rate law or rate equation or rate expression. Let us consider a reaction AA plus BB plus CC gives rise to product. See, for this reaction, according to law of mass action, rate can be written as directly proportional to the product of active masses of reactants, like concentration of A to the power A into B to the power B into C to the power C. Then this can be written as K into A power A into B power B into C power C. Okay. Now this is what is known as rate law or rate equation, rate expression. Now what is rate equation? See, it is an equation which relates rate of the reaction with the concentration of reactant. But writing this rate equation is, of course, very interesting. It is not that simple. Okay, let me also tell you one more point here itself. Now, taking the sum of the powers of concentration terms in the rate equation, remember, gives us the order of the reaction. So these two are very important. But let me give you some examples. And then let us decide on whether it is that easy or bit complex. Come on. Let me just give you the formation of hydrogen iodide. See, for this reaction, rate equation or a rate expression can be written as H2 to the power 1 into I2 to the power 1. So the overall order of the reaction is 2. Order with respect to hydrogen is 1. And even the order with respect to iodine is also 1. Okay. If you look at the powers in the rate equation, I mean powers of the concentration terms in the rate equation, they are simply the stoichiometric coefficients of hydrogen and iodine. Okay, let us take some other examples and see whether it is the same as in this case or is different. Yes. Now let me give you one more example. Considering this, look at the rate equation or rate expression. You may be surprised to see the powers, but they are absolutely correct. You know, these powers are obtained not just from the stoichiometric equation. Rather, they are obtained from the experimental facts, experimental data. Let me also give you one more example. See, in this case, of course, the order of reaction is zero, zeroth order reaction. Now let me go for the next one. This is much more interesting. Now for this, the rate expression or rate equation goes this way. Too much. See, the power here is half. But how? We'll tell you. See, here the order of the reaction is 3 by 2. Sum of the powers, 1 plus half. Order with respect to hydrogen is 1. And that with respect to bromine is half. But how? Let's see. But before that, let me give you a note. Now, if you consider the first one where the powers were the same as the stoichiometric coefficient, you know, that is a simple reaction. First, a simple reaction where the powers are the same as the stoichiometric coefficient. Whereas the second and third examples are complex. Whatever it may be, remember, rate equation or a rate expression should only be written by conducting experiments, not just by considering the stoichiometric equation. Rate equation should not be written, very important, considering the stoichiometric equation. But should be written by conducting experiments. Okay. Let me just get into some more deeper into the concept. Let us again consider this example and see how we get these powers. Because this is a bit interesting would like to take this one. Now, let us write the rate expression or a rate equation like this, without any powers first. Let us see what powers we get after conducting the experiment. Now, how to conduct experiments? It's very simple. If you want to know the effect of concentration of hydrogen on rate, keep the concentration of bromine as constant. Let this be the experiment number 1. Now, suppose the concentration of hydrogen is doubled. Anyway, the concentration of bromine is kept constant. If suppose the rate is doubled, you have doubled the concentration of hydrogen, upon which even the rate is also doubled. So the power here can be written as 2. Now suppose if the concentration of hydrogen is doubled and the rate say became 16 times, what is going to be the power? 4. Simple. Is that okay? Now let's see. Not just this, anything. Supposing if the concentration of hydrogen is tripled, and suppose if the rate becomes 27 times, what would be the power? 3. So that is how the powers are obtained, not simply by considering the stoichiometric coefficient. This is how you have to conduct experiments. Okay. But the actual thing what has happened with this particular reaction is, when concentration of hydrogen is doubled, rate just became double. So that is how we got the power as 1. So this is our experiment number 1. Now, say in the second experiment, to know the effect of concentration of bromine on rate, let us keep the concentration of hydrogen as constant. And anyway, you got clarity on how the powers are obtained. Let me just tell you what has actually happened. Now, when concentration of bromine is doubled, rate became root 2 times. When concentration of bromine is doubled, rate became root 2 times. So that is how the power is obtained here as half. Is that okay? In the first case, when concentration of hydrogen is doubled, rate is doubled. That is how we got this power 1. And in the second case, keeping the concentration of hydrogen as constant, when concentration of bromine is doubled, the rate simply got root 2 times. That is how we got the power. Hope you got my point. It is not just the stoichiometric coefficient that we have considered as powers. These powers are in fact obtained by conducting experiments. So rate equation should only be written after conducting experiments, not just by considering the stoichiometric equation. Okay, let me also give you one more example. Suppose if you consider this expression, see for this, the rate expression or rate equation is K into concentration of N2O5 to the power 1. See, I've written this 1 not because the stoichiometric coefficient is 1. No, no, no. I have written it considering the experimental data. That is how I got this power. Then suppose sometimes, if suppose it is given as this, what is going to be the rate expression for this? Will it be this? Will it be this? No, can never be. Because as far as this particular reaction is concerned, remember, when concentration of N2O5 is doubled, rate is only doubled. Can never be this, because when concentration of N2O5 is doubled, rate is never going to become 2 power 10 times. No, this is wrong. So just by changing the stoichiometric coefficient, if somebody tries to confuse you, don't get confused. Rather, if you want clarity, you have to ask them to give the experimental data. That is how you can, of course, get the powers. Hope this is clear. So the powers are obtained only from the experimental data. Simply, if somebody asks the order of a reaction, you don't answer to them. You ask them to provide the experimental data or the rate equation, which is generally obtained, which is of course obtained from the experimental data only, as I said. This is what is very interesting. Now let us take the units of rate constant or specific rate considering a general reaction. So for this, rate expression can be given as K into A power N, considering it as a simple reaction. So it can be written as K is equal to rate by A power n. We know that rate is a change in concentration by time. Then by A power n. Now, this is anyway concentration. In general, we consider molarity, mole per liter. By time, you can consider time or per second, let us say. So, mole per liter per second is a unit of rate by. See, this is molar concentration again. So, this can be given as mole per liter to the power n. Okay. Now, the final expression for the units of K can be given as liter to the power n minus 1 mole to the power 1 minus n per time or per second, where n is the order of the reaction. Okay. Next. Let us now discuss about zero order reaction. As I said, order is the sum of the powers of concentration terms in the rate equation. And see here, the sum of the powers is a 0. Sum of the powers of concentration terms is 0. So we can say a zero order reaction as something where the rate of reaction is independent of the concentration of reactant. See, the rate of reaction is independent of the concentration of reactant. It is known as zeroth order reaction. It can also be defined as a reaction in which rate of reaction depends on the zeroth power of concentration term. Zeroth power of concentration, nothing but independent of concentration. So both are next. Let us go for some mathematical expressions in this. Consider a reaction A gives rise to products. Now I told you very clearly not to see this one here. In this case, rate of the reaction with respect to A, nothing but minus D concentration of A by dt, is directly proportional to, see, this is nothing but rate. Rate of the reaction with respect to A, we know that, is directly proportional to the concentration of A to the power 0, right? Minus a dA by dt can be written as, now removing the proportionality, we can write a constant, K0 into A power 0. Of course, A power 0 is 1. So now it can be written as D concentration of A is equal to minus K0 into dt. Okay. Now taking that again, D concentration of A is equal to minus K0 into dt. See, on integration, we get A is equal to minus K0 into T plus constant, right? Now here, let us take some condition. Say at a time T is equal to 0. That means when you are about to start the reaction, the concentration of A, now when I say concentration of A, that is the concentration of A left is nothing but the concentration of A what you have started with, right? Because you are just about to start, you have not yet started. Now substituting this here in this expression, what do we get? See, we get the value of constant. Now T is equal to 0. A has become A naught. So then the constant, the value of constant will be equal to A naught. Now substituting this value of constant again in the same expression, it can be written as A is equal to minus K0T plus A naught. So considering that this condition, we got A as equal to A naught, of course, and then substituting this in this expression, we got constant. Now the constant is again substituted in the same expression. Come on, this can be written as K0 into T is equal to A naught minus A, and K0 can be written as A naught minus A by T. So this is the expression for the zeroth order rate constant. K0 refers to zeroth order rate constant. Okay.